Otherwise, your A-level teacher is going to have so much trouble. Okay. Question 7 is about equilibrium. Some people don't like equilibrium topic, yeah. They think it's difficult and stuff, but it really comes down to what is meant by equilibrium. Okay. All right. What is meant by dynamic equilibrium? In fact, that's what they're saying. Okay. Explain why the concentration of steam and hydrogen do not change. All right. So this is a consequence. This is a consequence, meaning it's a result. It's a result of what is happening. Basically, define dynamic equilibrium. Because the rate of the forward reaction becomes equal to the rate of the backward reaction at dynamic equilibrium or upon reaching dynamic equilibrium. Okay, dynamic equilibrium. As a result of that, the concentration of the reactor and the concentration of the product, they are not changing once you reach dynamic equilibrium. Okay, they do not need to be equal, but they do not change anymore. Okay, now the pressure of the equilibrium mixture is increased, but you keep temperature constant. Because you keep temperature constant, we don't have to worry about exothermic or endothermic. And they want to talk about composition of the equilibrium mixture. Here is very important. Equilibrium mixture. Did you realize the equilibrium mixture, they don't mention this or this or this or this in particular? They mention equilibrium mixture. That means you need to specify all of them. What happened to all of them? Okay, what happened to all of them? Because all of them are involved in the equilibrium mixture. Okay, they want to predict and explain. All right. The most important thing is you talk about pressure here. This is a solid. Solids are not affected by pressure as much as gas. We talk about gas laws. If you have done physics, you will have heard of Boyle's law, which said that pressure of a gas is inversely proportional to the volume of a gas, or PV equal to constant. This involves gases because pressure affects gases a lot. Okay, because we're dealing with gases, when we talk about pressure, we need to look at the moles of gases. We look at gases only because these are not gases, I can ignore them. Altogether, there are 4 moles of gas on the left. Altogether, there are 4 moles of gas on the right. Okay, so the equation, which is balanced, the equation above shows equal number of moles of gases. This is very important, yeah, gases on both sides of the equation, or you can say equilibrium. Okay, because of the equal number of moles of gases on both sides of the equation, so changing pressure, or in this case increasing pressure, in fact whether you decrease or increase, whether you change pressure or not, will not affect the equilibrium position. But that is not what they're asking for. Okay, what are they asking for? They're asking on the composition, right? If that do not affect the equilibrium position, therefore it will not change. It will not change the composition of the equilibrium mixture. Meaning to say, you can say that they stay the same, but I already said it will not change the composition, meaning they must stay the same, right? Now, you do not change pressure. Okay, you do not change pressure, but you increase the temperature. Temperature increase. Usually, when they talk about temperature, we need to know about the enthalpy change of the reaction, right? Whether it's exo or endo in the forward reaction. We are not given that information. Not there, not there. Are we given here? No. But that's not what they're asking. They're asking the position shift to the left side when temperature increase. Okay? I'm sure you've done the case study, Haber and contact process like 1,000 times. Well, I hope you've done it 1,000 times, because I have in my entire life, I think. Probably more than that. So what it's saying is, as temperature increase, the equilibrium shift to the left. Okay? As temperature increase, the equilibrium shift to the left. Okay? If we say, if the forward reaction is endo, okay? Only a hypothetical situation, yeah? If it absorbs heat in the forward reaction, when I increase temperature, the forward reaction will absorb more heat, so it will shift to the right. But I see the opposite, so that means my assumption must be opposite. That means this assumption was wrong. It must be opposite. Therefore, the enthalpy change of the reaction, the enthalpy change of the forward reaction must be endo. Sorry, not endo, opposite. Must be exothermic. It's worth it to double check, alright? You can think about your Haber process, which is exothermic in the forward reaction. You can think about your contact process, which is exothermic in the forward reaction. When you increase temperature, you know you will get the equilibrium shifting to the left. Because when the forward reaction is exothermic, it means the reaction will release heat. When you increase temperature, the equilibrium will try to oppose the change. It will try to decrease the temperature. That means it will release less heat. How would the equilibrium release less heat? Well, it will favor this side, to the left, by forming less product. When you favor to the left, when you shift to the left, it will release less heat. Oh, guess what? It shifts to the left when temperature increase. Therefore, our reasoning was correct. Okay? Now they want to talk about rate. When you talk about rate, there is nothing to do with equilibrium. So do not go and say anything about equilibrium there, okay? You're going to explain internal collision theory. So as temperature increases, I've used T there, perhaps you should use temperature, rate of reaction will increase. You do not stop there. The question actually asks you to explain, right? Okay, because reacting particles, which include the solid and the gas, will increase in kinetic energy, collides more frequently. But you know, with temperature, that is not all, yeah? I know it's only 1 mark, but it's very good practice to know the other factor as well. Also, your proportion of reacting particles, and you never know when it's going to be 2 marks. Probably next time, you know, when you forget about it, you can be 2 marks and then you forget this other point, all right? So it's very important to include both points. Also, the proportion of reacting molecules with sufficient energy or with enough energy greater than or equal to the activation energy will increase. Therefore, more effective collision. So I like this word called effective collision. You might have learned it in school as successful collisions. When you have more successful collision or more effective collisions, your rate will increase, yeah? For obvious reason, I hope. So this is an equilibrium question. They say, why is it important to have a closed system? So the system refers to the equilibrium itself, the reaction or the equilibrium itself. Why do you want it for dynamic equilibrium? If you don't have a closed system, the reactants and products can escape. Okay, the reactants or products, both gaseous. See equation above. So you can see they are all gaseous, right? So if you don't close it up, the reactants or products can escape because they are gaseous, yeah? So the pressure of the equilibrium mixture is decreased, but temperature constant. So temperature is constant, is to do with pressure. They want composition of equilibrium mixture. So composition is not the same as position. Alright, if you look at equilibrium, from left to right is called forward reaction. Reactant is going to product is called forward reaction. Product going to reactants, right to left, is called backward reaction. They want the composition of the mixture. Did they specify this or this or this? No, they didn't. They want composition of the equilibrium mixture. This whole thing is the equilibrium mixture. What does it mean then? It means you have to talk about this, this, and this, all of them, because they are all part of the equilibrium mixture. So you got to read the question carefully, yeah? Because this is to do with equilibrium, and we're talking about pressure, you need to think about the number of gaseous molecules based on the number of moles of gases on the left and on the right. Here you have 2 moles plus 1 mole. You have 3 moles of gases. Gases are very important, especially we're talking about pressure. So there are only 2 moles of gases on the right hand side. Okay, I'm going to start explaining first. So 3 moles of gases on the left side of equation, only 2 moles of gases on the right side. So when you decrease pressure, will mean the system, or you can talk about the equilibrium, will try to oppose the change. You are decreasing pressure, so the system will want to increase pressure. Gases exert more pressure than solid or liquid. That's why we're looking at gases all the time. When you want to increase pressure, you want to go to the side with more gaseous molecule, because more gaseous molecule would mean they exert more pressure on the walls of the container of the closed system. Pressure is force over area. When you exert more force over the area of the walls of the container, they're going to increase the pressure. They're going to do to oppose this change. All right. So decreased pressure will mean the system shift to favor the side with more gaseous molecule, because you want to increase the pressure again. Yeah. As a result of you decreasing the pressure, you will move to the side with more gaseous molecule. Therefore, equilibrium shift to there are more gaseous molecule here, right? So it will shift backward. It will shift to the left, or you can say favor backward reaction. Okay, so that means when it favor backward reaction, if it's gonna favor backward reactions, then your composition mixture will have more NO, more O2, lesser NO2. Okay, I hope that makes sense. All right, you can talk about more, or you can talk about higher concentration of NO and O2, lower concentration of NO2. Same thing, yeah? But you got to talk about all 3 of them, because they mention composition of the equilibrium mixture. They did not specify any one. Okay, be careful, yeah? Next bit, you keep the pressure constant, but you decrease temperature. So temperature decrease, it favor the right. Temperature decrease, it favor the right. This tells you the enthalpy change of you got to specify a forward reaction. So from left to right is, well, let's think about it. When you decrease temperature, when you lower temperature, equilibrium shift to the right. When you lower temperature, the equilibrium will try to increase temperature. It will shift to the right. So does that mean it absorbs more heat energy? Not really, because you actually decrease temperature, right? So it's got to be exothermic. That means it releases heat in the forward reaction. When you decrease temperature, the forward reaction will try to release more heat, because it wants to increase temperature to oppose the change, which was decreasing temperature. So that's how I know the forward reaction is exothermic. You must have encountered this in your Haber process, where the forward reaction is exothermic as well. So when you decrease temperature, it actually shifts to the right. Okay? You are decreasing temperature. Why the rate of reaction decrease? So there are 2 factors here. Temperature is a measure of kinetic energy, which is half mv squared. That is to do with your velocity of the reacting particles, how fast they move. Okay? So as temperature decreases, particles, reacting particles, have lesser kinetic energy, therefore move slower, collide less frequently. So that's the first bit on collision frequency. But the second bit is also quite important, as temperature also. So this is additionally, so I don't have to say temperature decrease again. So that means continue from here. As temperature decrease, also the proportion of reacting particles having enough energy, having enough, or you can say sufficient or enough energy greater than or equal to the activation energy of the reaction will decrease. Therefore, lesser effective. You can say effective, or you can use the word successful collision. Overall, rate decreases. So how fast the reaction goes, it decreases, becomes slower. This is an equilibrium question. They want you to describe how and also explain why it changes. You have decreased temperature, you keep pressure constant. So we are not going to talk about pressure here. The forward reaction is exothermic. The forward reaction is exothermic. So when temperature decreases, because you decrease temperature, what will the forward reaction do? What will the equilibrium do? The equilibrium will try to oppose that change. It will try to increase the temperature, by you release heat in the forward reaction, right? You are exothermic in the forward reaction. When you decrease temperature, the forward reaction will release more heat because you want to increase temperature. That is Le Chatelier principle, saying that in an equilibrium, when you introduce a change, the equilibrium will try to oppose that change. This is the change. The equilibrium will try to go against it to increase temperature. Because you release heat, so I will release more heat because I want to increase temperature. How do I increase more heat? Therefore, the equilibrium position will shift to the right because I want to release more heat. Okay, they are not asking on the yield, they're asking on position. Alright, I have stated how the position will change, but I started by explaining it first. It does not matter. Explain and also stating, as long as I address everything. Now you increase pressure, but you keep temperature constant. Why it has no effect? These are gaseous reaction. Have a look. I'm going to change color now. This, and this. They are all gaseous, right? Okay. So how many mole of gas do you have? You have 1. You have 1 plus 1. You have 2 moles of gases on the left hand side. You have 1 there and you have 1 there. When they don't show a number in front, that means you only have 1 plus 1. I mean 1 only. So there's 2 moles of gases on the right hand side. You have equal number of moles of gases. The gases are very important because we are talking about pressure. If you have a solid, pressure is not going to affect solid that much at all. Same total number of moles of gases on both sides of the equilibrium. So there's 2 moles of gases on the left, 2 moles of gases on the right. Therefore, no effect by pressure, no effect on equilibrium position, okay, as pressure changes.